a lot of people wonder how much earlier can you see the sunrise if you walk on top of a high-story building, or for instance if you're on a mountain. And similarly, how much later can you still see the sunset? If the sunset for you when you were standing on the ground, can you still run a few flights up and see the sun again? It turns out that calculating this is not so difficult, and all you need to know is Pythagorean theorem. So here is the simple approximation. I'm going to assume we're standing at the equator at the feet of 100, at the height of 100 meters, for simplicity's sake, something like a 24-story building. I'm going to use metric system as opposed to feet for simplicity. So you're at 100 meters up, and you want to know this distance x, how far you are from a place where the sun can be seen from the ground. R is 6,000 kilometers. That is the radius of the Earth. So r squared plus x squared equals r plus 0.1 kilometer squared. All right, 100 meters is 1/10 of a kilometer. So the 0.1 squared can be neglected, and r squared and r squared cancel out. So basically x squared is 2 times 0.1 times r, which is 1200 kilometers. So according to this, x is 35, approximately 35 kilometers. So that's the distance from a place where you could see the sun on the horizon, and a place where you could see the sun on the horizon when you're 100 meters above the ground. So if you're on the equator, the approximate parallel of the Earth there, the circumference is 2 pi r, so it's 6,000 kilometers times approximately 6, so it's 36,000 kilometers. So 35 kilometers out of 36,000 is approximately 1 in 1,000. So the amount of time that the sun goes around the Earth is 24 hours, so 1,000th of that 24 hours divided by 1,000 will give you approximately 1.5 minutes. So if you go up 25 floors, you could go do it on the elevator, you could still catch the sundown. If you just saw the sundown on the ground, you may be able to catch. But as you could see here, the difference between seeing the sundown at the ground and on a certain height goes as square, meaning the higher you are, the less the difference is in terms of, less proportionate the difference is. Meaning if it's just a few meters above the ground, the difference is quite a number of seconds. You could easily get to the first floor and still see the sundown. In order to see the sundown on 25th floor, you'd need to use an elevator. On the other hand, in order to see the sundown on Himalayas, which would give you something like 15-minute difference, there you won't be able to get at all. If you saw sundown at the feet of Himalayas, if it was possible, to get 8 kilometers up within 15 minutes is simply impossible, unless you have some really fast ways of moving. Another interesting, of course, like I said, the previous calculation was based on the equator. When it's further north, the difference is greater. And in terms of if one is wondering, if one wants to pray, for instance, with sunrise, what we call Vasikin prayer, what do you do if you're high up? Well, buildings usually don't count, but if you live on a mountain and there is plain sea level around you, then in fact you would have to daven ideally a little bit earlier than if you'd be on the ground. But if everything around you is also high up, then the difference is negligible. If, for instance, both U are high above the sea level, but in the east as well, it's high above sea level, then the sunrise is almost the same as if you would be on the sea level. So in practice, sites like Maizmanim allow you to input how high you are and how high is the east horizon or the west horizon is, and they would give you then the calculation of sunrise and sundown according to these numbers. Now there's an interesting other corollary of this Pythagorean theorem. Surprisingly enough, it's one of those theorems that has lots of proofs and lots of interesting parallels and corollaries. It's mentioned, by the way, in Chazon Ish's writings and in the Rishonim already. It's a well-known theorem, and it's used for various practical questions in Jewish law as well. But one thing that you might ask theoretically, what's the first cosmic speed? Meaning at what speed you'd have to go around the Earth in order that you wouldn't be falling, right? This is the speed at which the space shuttles are circling the Earth. They don't fly usually very high up. They're not more than a few dozen miles above the Earth. So we'll assume that they're about the same distance, and it's the same formula actually. So we'll assume they're about, assuming there would be no air resistance. So here is how it flies, and we want to know how much distance x should it fly in the first second in order to fall exactly to be just above the ground, just like before. So this amount that it falls within the first second is the same for any body. Whether if there is no air resistance, it doesn't matter if it's a shuttle, if it's a person jumping into the swimming pool. In the first second, we would fly about 5 meters down if there would be no air resistance. The reason for this is that the G constant, 32 feet per square second, in metric system it's 9.8 feet per meters per square second. So what that means is that if you start with 0 speed going down, you jump from a certain high point to the swimming pool, let's say, within the first second your speed will be 10 meters per second. So the average speed is 5. You started with 0, ended with 10, so it's 5. So basically go down by 5 meters. So this number is 5, which is in kilometers 0.005. And the formula is exactly the same. It's again r squared plus x squared equals r plus 0.005 squared. So it's exactly the same equation we're solving, and it's exactly the same story here. So 2 times 0.005 times r, which comes out to 60. Right? 6,000 times 0.005 times 2 is 60. And that's x squared. So square root of 60 is approximately 7 point something. And that's indeed what the first cosmic speed is, 7.9 kilometers per second. You have to fly this distance x, 7 point something kilometers, and go down 5 meters in order to stay at the same distance from the Earth.